So here I am, no baby yet. We are still in a holding pattern. So I'll keep you updated as things move along. Go ahead.
What's the due date again?
Tomorrow.
Oh wow.
Yeah. So we are waiting to see what will happen. But it is likely that we will not have a lab for us this week. But we'll cross that bridge when we get there. And of course, I'll keep you updated as time continues. I was checking in on Alex this morning. It seems like about 20% of you have already done the work due tomorrow midnight, and lots of you are on the way. Those of you that haven't started yet, it looks like maybe there's just one person who hasn't started yet, do be reminded that you'll have to complete the knowledge check from last week before you can continue on with this week's objectives. So you may have a bit of extra work to do. The knowledge check takes a while. Let's see, looking here, it took some people about an hour, some people 25 minutes. It seems to be a wide range. So just plan accordingly as you check in with Alex this week. I mentioned on Friday that Alex, not for this week, but for next week, finishes out chapter 3. I don't know that we'll get all the way through chapter 3 material today, but we will do our best just in case we do not have any lecture on Friday this week. So let's get back into it. We left last time talking about doing some stoichiometric calculations. So here we have the calculation we did with sugar and figuring out how much CO2 would be generated given eating a certain amount of sugar. So hopefully this box, right? Remember that we draw this box to move from the mass in grams of one compound through to moles of that compound. We use this mole to mole ratio given in the balanced equation to convert to moles of the second compound, and then we finally solve for the mass of the second compound. Let's try another one. This example tells us that alkali metals react with water to make hydrogen gas and the alkali metal hydroxide. Typical reaction is between lithium and water. So if we have lithium and water, it tells us we're going to make hydrogen gas and alkali metal hydroxide. So hydrogen gas, what's the formula?
H2.
H2, yeah. Oops. Yeah, remember it's our diatomic. And so that's going to be H2. And alkali metal hydroxide, well, our alkali metal is lithium. What's hydroxide mean?
OH negative.
That's right. Lithium's a 1+, hydroxide's a 1 negative, so we just end up with LiOH. And so this question asks us how many grams of lithium, so we don't know. How many grams of lithium do we need to make 9.89 grams of hydrogen? We're going to make our box again to moles of hydrogen, moles of lithium, and grams of lithium. What do we need to do before we begin our our adventure.
Assume they're 100 grams.
We don't need to assume 100 grams for this one. We're actually going to start with this 9.89, but we need to do what to make sure that our reaction is correct?
Balance our equation.
Absolutely. We got to balance this bad boy. So we have one lithium on the left, one lithium on the right. That seems okay. We have 2 hydrogen atoms on the left. Right now we have 3 hydrogen atoms on the right. If I want to make it so that it's an even number on both sides, I shouldn't add a coefficient in front of the H2 because that will keep it an odd number, since over here we only have 1. So let's double this real quick. We'll put a 2 in front of lithium hydroxide. So that gives us a total of 4 hydrogens, 2 from H2 and then 2 from lithium hydroxide. That's 4 hydrogens on the right, so we need a 2 here. So we have 4 total hydrogens on the left. That gives us 2 oxygens. We have 2 oxygens from lithium hydroxide. Now 2 lithium, so we need a 2 here in front of our lithium. Often it will be easiest to balance the elements that are by themselves last, because if you change their coefficient, it doesn't change any of the other elements in your equation. And so saving lithium and hydrogen until last will help us to balance that equation. Okay. All right. So now we're going to make our conversion factors. All right. 9.89 grams of hydrogen. What's the molar mass of hydrogen?
1.01.
1.008.
Be careful. That's the molar mass of an atom of hydrogen. Is that
2.02.
hydrogen gas? Julia?
2.02.
Yeah, 2.02 grams is the molar mass for hydrogen gas, since it's H2. Okay. So do be careful doubling that periodic table mass, that average atomic mass, for diatomic elements. What's our mole to mole ratio for lithium to hydrogen?
2 to 1.
2 to 1, yeah, 2 moles of lithium for every mole of hydrogen. And then we need the molar mass of lithium from the periodic table.
6.94.
6.94 grams of lithium for every mole of lithium. Right. If we do a quick double check of our units, grams hydrogen on the top, grams hydrogen on the bottom, mole hydrogen on top and bottom, mole lithium on top and bottom, left with grams of lithium. That's what it asks for. Oops. We go ahead and work it out, and what do we end up with?
68.0 grams of lithium.
68.0 grams of lithium. Okay. I got 68.1, rounding differentiation somewhere. I used 2.016 instead of 2.02, not a big deal. But you know, you may be off a little bit in that last significant figure. All right. Okay. So again, that's just using stoichiometry, going back and forth between grams of one component and another component in our chemical equation. We got to make sure it's balanced before we start start moving along our box. Okay. So up to now, when we have talked about these reactions, we've said, you know, this burns in oxygen, so there's lots of oxygen left over. Or this is dissolved in water, and so there's plenty of extra water left over. And so we haven't ever worried about having enough of the second reactant. However, oftentimes we want to do a reaction where maybe a particular reactant is hugely expensive, right? Maybe we're doing a reaction with gold or platinum or ruthenium or something. Or maybe we're doing a reaction where we're reacting a compound that is very rare. Maybe we made one of the reactants, we synthesized it in lab and we only have 10 milligrams and we want to make sure that we use all 10 milligrams up and that none is left unreacted. That's when limiting reagent comes into play. A limiting reagent or limiting reactant, those terms are interchangeable. A limiting reagent, limiting reactant, that is the reactant that limits how much product can be made. A common example is to think about something like a bicycle, right? If you had 10 bicycle frames, you had 10 handlebars, you had 10 seats, and you had 10 wheels. How many bicycles could you make?
5.
Yeah, we can only make 5 bicycles because each bicycle requires 2 wheels. And so if we think about the equation, the bicycle equation, right? It might be 1 frame plus 1 handlebar plus 1 seat plus 2 wheels gives us 1 bicycle, right? And so we have to have that balanced equation in order to know that we can only make 5 bicycles given 10 of everything, right? If we didn't know that every bicycle had 2 wheels, then we might think we could make 10 bicycles from 10 pieces of everything. And so limiting reactant is the reactant that limits how much of a product we can make. And so in this example, between the frame, handlebars, seats, and wheels, which of those 4 is our limiting reactant?
Wheels.
The wheels, absolutely, right? These guys limit how many bicycles we can make. In this example that's in the boxes over here, we start with hydrogen and carbon monoxide, and we react those together to make methanol, CH3OH. This is a proposed way of dealing with some greenhouse gases. Carbon monoxide is a pretty nasty greenhouse gas and poisonous to boot. And so based on what we have before, we have 6 molecules of hydrogen. Those are the light gray ones. We have 4 molecules of CO. That's the black and red. Afterwards, you can tell we have 3 molecules of methanol. And then we have this leftover molecule of carbon monoxide. And so in this example, what was our limiting reagent? The carbon monoxide or the hydrogen?
Hydrogen.
The hydrogen, because we didn't have enough to convert all of that carbon monoxide into methanol. And so hydrogen was our limiting reactant. Of course, if this were a real world scenario, we would want it to be the exact opposite. We'd want hydrogen to be in excess so that we react away every molecule of carbon monoxide. When we go about solving limiting reactant problems, there are a couple ways that we can do it. Of course, you can stop with moles if you want, but generally speaking, the questions ask for, rarely do questions just ask what's the limiting reagent, right? If that's true, you can stop with the number of moles of a given reactant or of a given product. Usually, however, they ask for a number of grams of a product that are made, or grams of a reactant that are used. And so here we have an equation between ammonia and carbon dioxide, where we make this urea compound, NH2,2CO, and water's left over. And so the first thing we want to do is figure out what the limiting reactant is. And so really we're going to make two boxes, right? Just like before, we made a box going to from a reactant to a product or vice versa. We're going to make two boxes, one for each starting material. And this time I'm going to leave the actual drawing of the box out of it and see if you can follow along. Right? So we start with the grams of NH3, 637.2 grams of NH3. 1 mole of NH3 is 17.04 grams of NH3. And then from our balanced equation, we know that 1 mole of urea requires 2 moles of ammonia, NH3. And I'm going to go all the way to grams. Like I said, oftentimes a question will ask you for grams. And so I'm going to go all the way. And so 1 mole of urea, NH2,2CO, that's 14 times 2 is 28, plus 4 is 32, plus 12 is 46, plus 16 is 62. 0.22, 3, 4, 5, 6, 7, 62.07 grams of urea. Oops. I'm off. Oops. 60.06. All right, so we plug this into our calculator. 637.2 divided by 17.04 times, so divided by 2 times 60.06 gives us 1,123 grams of urea. So let's do the same for CO2, carbon dioxide. 1,142 grams of carbon dioxide. We're going to convert that to moles. 44.02 grams of CO2 per mole. There's 1 mole of urea. For every mole of carbon dioxide. And again, it's the same molar mass, 60.06 grams of urea for every mole of urea. When we do this, 1142 divided by 44.02 times 60.06, we end up with 1,558 grams of urea. Hopefully you got very similar numbers. when we look at these, how do we decide which one is our limiting reagent?
The one that made less.
That's right, the one that produced less of our product. And so 1123 is less than 1558. So ammonia, MH3, is our limiting reactant. Right? Now in this case, ammonia had the smaller number of grams, and so you might have been tempted to just go, there's less ammonia, so it must be the limiting reagent. But that's not always the case. Another thing that I want to point out, we could have stopped here. Oops, wait a minute. We could have stopped at this point with moles of urea, right? Because we could compare the number of moles just like we can compare the number of grams. However, because most questions will ask us how many grams of product are obtained or something along those lines, it's always useful to go to the grams. Now I did it for urea, but I could have just as easily done it for water, right? Water is another product, and if we had figured out how many grams of water, we could have compared those two numbers, and of course we would still choose the smaller number to determine which was the limiting reactant. Right? I happen to know that the next slide is going to ask us, calculate the mass of urea formed. Well, we just did that, right? Like I said, a lot of times these questions won't stop at what is the limiting reactant, but rather how much of a product is formed. So how much urea is formed? Well, we just said 1,123 grams of urea. And so you've already got that question solved because you've determined the number of grams when you calculated the limiting reactant. Okay, so let me scoot back one slide. Any questions on what we did here? We're just filling out that box for each reactant going to the same product. If I had done ammonia to urea and then CO2 to water, I cannot compare those numbers because I didn't go to the same product. You've got to go to the same product from both reactants. Now the last part of this question asks how much excess reagent is left at the end of the reaction. So there are a couple of ways to approach this problem. I'm going to show you the way that I think is the easier of the two, and then I'll talk you through the other one. To me, it's easier to start with how much you actually made. Right? So start with actual amount produced. Okay. So if we start with 1,123 grams of urea, we just have to work backwards to figure out how many grams of CO2 that would have required. So if we work backwards, we flip all of our conversion factors. So 1 mole of NH2CO with 60.06 grams of NH2CO. There's 1 mole of carbon dioxide for every mole of urea. And there's 44.02 grams of carbon dioxide for every mole of carbon dioxide. We do this, we end up with 1123 divided by 60.06 times 44.02, 823.1 grams of CO2. Now, is that how much is left over?
No, it's how much we used.
Yeah, that's how much we used. Let's remember here that we started with 1142 grams of carbon dioxide, and so then we have to subtract. So let me do this in a different color. 1142 initial minus 823.1 used gives us 318.9 that remain. Our sig fig rules tell us that's 319 grams of CO2 that are left over. Okay, so let me add here. You start with the actual amount produced, work backwards, and then subtract. Right? You can do it by taking the difference in the amount of urea that was originally produced. So let me jump back 2 slides here. Right. We can take a difference in 1,123 and 1,558. Take that difference, and then with the difference, work backwards. So subtract at the beginning, and then work backwards. And then what you have is the amount left over, right? That's the difference between how much you could have made with CO2 and how much you actually made based on ammonia. And so you can do it by subtracting initially, then working backwards to get the amount left over. So that's another way of doing it, but approaching it either way is absolutely fine. Students like to forget this step here, so don't forget to subtract it from how much you originally started with. Questions on that limiting reactant, limiting reagent stuff? Okay. So let's try one more then. We have a reaction between methanol and this compound methyl bromide. That's a real funny way of naming it. That's an organic nomenclature. We don't have to worry about that in this class. It forms dimethyl ether as well as some other stuff. So they've given us the whole reaction here. How many grams of this methyl bromide and this lithium butane, butyllithium, is necessary to carry out this reaction if we start with 10 grams of methanol? So this is not a limiting reactant problem, but it's one where we still need 2 different boxes, right? We start with 10 grams of methanol, and I want to know how many grams of methyl bromide and how many grams of this butyllithium compound. So what I'm going to do is I'm going to give you a few minutes to work through that on your own. Actually, here's what I'll do. I'm just going to quickly generate us some breakout rooms. You can work together in there, and we can see how we're doing in terms of calculating these amounts. $12 and 4, 16, and 16 is 32. 32 plus 1, 2, 3, 4, 5. It's balanced. Yes, sir.
So we joined the breakout room before we could get the problem done.
Okay. So the slides are on Moodle if you ever want to follow along. Yeah, so that's going to be the easiest way for me to do that with you.
Okay.
Let me see here.
So go to middle.
Yeah, and pull the slides off of there.
Okay.
Going to be the easiest way for you to see that without me. Oops. Okay. All right. Hopefully you made some progress. Did we figure out how much methyl bromide or butyl lithium were required?
We got 29.6 for CH3BR.
Excellent. Sounds good.
And for the lithium, I don't know what that is. Methanol, is that what that is?
That's based on butane, so we call that butyl
Oh.
lithium. Yeah.
Butyl lithium. Okay, it's 50 grams.
50 seems big.
Oh.
I got 20.
We had 20.
Uh-oh.
Yeah. I got 20 as well.
How did you, may I ask how you got that, please?
Yeah, sure.
Okay.
So here we go.
Huh. Oh, I see. Okay. I just put 2.5 moles for mine.
Yeah. So the textbook question actually has 2.5 moles there, because the butyl lithium in this case is what we call something that's not required for the reaction. It's what we call a catalyst. Right? It's just helping the reaction go on.
Yes, sir.
And so you don't really need the lithium. It's not part of the reaction that you're interested in, right? Because what you want to do, what they want to do in this example is make the they want to make this CH3OCH3, this dimethyl ether. They don't care a whole lot about the lithium. It's just there as a helper, essentially. And so, yeah, the question out of the textbook says, because we don't want the lithium to be the limiting reagent, we add 2.5 times what's necessary. And if you add 2.5 times what's necessary, then you go from 20 to 50 grams. Absolutely.
Yes, sir. All right. Thank you so much.
Sure. All right. So if you ended up with 29.6 and 20 grams, then we're on good ground here. Okay. All right. So the last thing to talk about to discuss in chapter 3 is this idea of reaction yield. What we've been calculating really so far are reaction yields. If I start with this much, how much of the product will I make? And so when we think about yields, we think about it in terms of a theoretical yield, which is what we have been calculating. And that's the calculated amount of a product given the amounts of the reactants. Okay, so as long as we know the amount of our reactant or reactants, we can figure out how much of a product we should end up with. Okay. And then there's the actual yield. Right, which is the amount of product produced in a reaction. And these two could be different for lots of reasons. In organic chemistry, especially where you're making new materials, sometimes if you put A and B together, you really want them to make C, but they might make D or E instead. And so you have what are called side reactions, reactions that you don't want to happen, but they happen anyway. And so that can limit the amount of product that you actually end up making. And so when we talk about yield, we're talking about how much did we get relative to how much we expected to get. And we call that the percent yield. And so to calculate the percent yield, that's going to be our actual divided by the theoretical. And since it's a percent, we're going to multiply it by 100. And this tells us sort of how good our reaction is. It tells us how well A and B are actually making C. All right. In this last example, we're going to sort of bring in the ideas of limiting reagent and percent yield in a couple of slides here. And so we start with some really large amounts of titanium chloride, titanium 4 chloride, and magnesium, right? Our goal is to make solid titanium. So we have titanium 4 chloride and some magnesium. We're going to react these two together. So we get magnesium chloride and titanium. We're going to calculate the theoretical yield in grams. What's the first step to doing this?
I have a quick question. Sorry.
Yeah, go ahead.
So percent yield, is it the higher the percent, the better the reaction, or is it the lower the percent, the better reaction?
No. We want a higher percent yield.
Okay. Thank you.
Absolutely. No, good question. Yeah. There are some organic syntheses, right, to make medicines and things like that might have 10 or 12 steps. And if you only have 50% yield in each step, then by the time you're at the 10th step, you're at less than 1% of what you started with. And so, the better yield you get, the higher yield you get, the better. Absolutely. All right. So, in calculating a theoretical yield, we're given the mass of both reactants. What's the first thing we have to do? Do we know which one of these is our limiting reagent? No. Right? No. So the first step is to determine the limiting reagent. Right. Even though the question doesn't ask us what's the limiting reagent, and really we don't need to know what the limiting reagent is, it's good to think about this in terms of a limiting reagent problem because we need to calculate how much titanium is made both from the titanium 4 chloride and from the magnesium. If you had to take a guess, which one would be the limiting reagent, the titanium 4 chloride or the magnesium? Which one makes sense? If we're trying to get pure titanium out, we'd rather have extra titanium or extra magnesium?
Magnesium.
Yeah, absolutely. If we have extra magnesium, that means we've reacted the titanium chloride all the way. We've gotten as much titanium out of it as we can, and we have a little magnesium left over. And so absolutely, it makes sense that the magnesium would be our excess reagent, the titanium 4 chloride, our limiting reagent. So let's do the math and figure it out. Right. This is just good practice. I know these problems seem perhaps a bit repetitive, but it's good practice for next week's quest.
Do we have a quest this week?
We will have a quest this week. If I am not there to proctor it, then our TA, Ryan, will give it to you. And it could be that it is via Alex this week. I plan for it to be via Moodle. But if, things get too crazy, giving it in Alex is a little bit easier. So expect a Moodle quiz at 2:30 on Thursday, but I can say with some certainty that we will not have a lab afterwards. All right. So we end up with a lot of titanium, 8.9. I'll take an extra sig fig, 3.5 times 10 to the 6th grams of titanium. Has anybody done it for the magnesium?
One point one one times 10 to the 7th.
1.11.
That's what I got.
Okay. Times 10 to the 7th grams of titanium. If we start with our 1.13 times 10 to the 7 grams of magnesium. All right. That makes some sense. Those are about the same mass, right? And magnesium is about half as heavy as titanium. And so that seems like a reasonable number. So which is our limiting reactant? The magnesium or the titanium?
Titanium.
Yeah, absolutely. So this titanium chloride is our limiting reactant. And so our theoretical yield is 8.935 times 10 to the 6th grams of titanium. Let's carry that forward. 8.935 times 10 to the 6th grams of titanium. And it says to calculate the percent yield if we had 7.91 times 10 to the 6th grams of titanium actually obtained. So our percent yield is 7.91 times 10 to the 6th grams divided by 8.935 times 10 to the 6th grams times 100%. We plug that in, 7.91 times 10 to the 6th divided by 8.935 times 10 to the 6th. And what did you get as your percent yield?
88.5%.
Yeah, 88.5%. Right? There's no unit on that other than percent. It is rare for you to find a percent yield greater than 100 in a textbook problem. In the lab, maybe it's a little more rare. Maybe it's a little more common due to other circumstances. I'm sure that in organic lab, you will discuss those things. But our percent yield's 88.5%. Again, no unit more than just percent there. Okay. All right, that is the end of chapter 3 material. So you should be all set for the next week. Hopefully I see you between now and then. But if not, of course, shoot me an email with any questions. If you want to schedule a Zoom, of course, you can do that at the appointment link that's on our Moodle page, I'll keep you updated about office hours on Wednesday and about the quest on Thursday. All right? Any questions before we head out?
No, sir.
All right. Y'all all have a good one.
Thank you.
Thank
You
you.
too. Have a fantastic day.
Dr. Davis, I had